Okay, we start out here with a function. We want to find the coordinates of the marked points here. And I've drawn an arrow here, a line and an arrow. So we got a y equals 0, meaning that this is the x-axis. Okay, so these points are on the x-axis. So for these points, y equals 0. Now, everybody that's here, and I don't know where everybody else is, but the half the class that's here understands then that we're going to set y equal to 0, and we're going to get the equation 0 equals negative 2x squared plus 12x minus 10. Okay, well, that's a quadratic equation. And without rewriting it, actually, I better leave it there. We can rewrite it so that the quadratic expression is on the left and it's equal to 0, just because that's going to be a little more familiar than having 0 on this side, but it really doesn't matter. You can still identify A, B, and C. So A equals negative 2, B equals 12, C equals negative 10. So that mark points y equals 0. So x equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a, which is then negative 12 plus or minus the square root of 144, and 4ac is 80. Got that right? Yeah. Well, let's spread it out. 4 times negative 2 times negative 10. All divided by 2 times negative 2. If I work this out, this is 144 minus 80, which is 64. So I went to the trouble to give you a perfect square here. It won't always be a perfect square, but get the idea. Using somewhat simpler numbers than you would always have, than you would sometimes have. So that's 12 plus or minus 8 over 4, negative 12 plus or minus 8, which is negative 20 over negative 4, I lost my negative there, or negative 4 over negative 4. And that's 5, 4, 1. Okay, so these points, if I've done this correctly, we'll check in a minute. This point would be the point find a safe place to label it. One, 0, we call that an x-intercept because it's on the x-axis. And 5, 0. Okay. And let me just back there and get your papers and hopefully, let's see. We're out of focus here. I'm using the wrong angle on camera. I thought it was in focus, but I'm going to switch cameras so we can see what I just did better. Now I'm going to move this over so we can see it all. But there it is. Okay, that's one thing you have to understand about a quadratic function. The x-axis is y equals 0. So if you want to find where this thing crosses the x-axis, you let y equals 0. You ignore the f of x and just write y equals this. But if I want to talk about this function, then I'm going to use f of x as the name of the function. But it doesn't come into this equation. All right, so that's really pretty straightforward. Now, the harder thing to do, or maybe the more complicated thing to do, is find the axis of symmetry. And there are two ways to find the axis of symmetry. One way is this thing is symmetric. It's a parabola. It's symmetric about an axis. So that this point is exactly as far to the right of the axis as this point is to the left. Same for any point. For any given y, you get a point here and a point here, and they split the difference. This distance, I didn't quite say that right, but you understand what I mean. This point's as far to the right as this one is to the left. There's an extra wobble in here. It actually looks like the peak of this thing is a little bit to the right. That's just an anomaly of my interaction between chalk and blackboard and brain. Okay. So there's a little glitch there, a little bump there. But you can kind of ignore that. There's a picture. Here's your axis of symmetry. What's the equation of that axis of symmetry? Well, x is 1 here, x is 5 here. We could sketch a couple of vertical dotted lines to emphasize what we understand. If this is a line where x equals 1, and this is a line where x equals 5. What's halfway between the line where x equals 1 and the line where x equals 5? It's going to be the line where x equals 3. That's the axis of symmetry. So if you know your zeros, you can find the axis of symmetry. There's another way to find the axis of symmetry. Let's just check. Okay. The other way that I talked about last time is you look at the quadratic formula, and this much of it gives you the axis of symmetry. So make sure I've got room here. Axis of symmetry is halfway between the zeros. Axis of symmetry is halfway between. To get the number halfway between two numbers, you can add them and divide by 2. You don't need to do that if you got 1 and 5. You can tell that 3 is halfway between there if you have any number sense at all. If you don't, you can still do the addition. Okay? If you got more complicated numbers, it's not going to be obvious what this number ought to be. And then you can add and divide by 2. So that's one way to get the axis of symmetry. Another way to get the axis of symmetry, if you want to get it first, and one of you did that, okay, is you use this. X equals negative b over 2a. Well, that's negative 12 over 4, right? Negative 12 over negative 4. And lo and behold, that's 3. So it's the line x equals 3. That makes sense? So that's easy. Now, I could have asked, but I was happy if you could find this. And if you went ahead and used what we did last time and found the vertex, that's just as good, although it's not what I asked. Okay? And if you found the vertex and didn't know how to find these, now you know how to find these. Okay? And if you found these, but didn't find the axis, find the vertex, maybe you knew how because I didn't ask and you didn't, you probably didn't do it. But in case you don't know, let's find it. Okay, so the vertex of course, is here. So what's the vertex? I'm going to have to move this point over a little further. Okay, so the vertex is on the axis of symmetry. So I need a little more sophisticated terminology. How I said I called this f of x for a reason, because now I want to say it's at the point 3, f of 3. Now, all that's saying is, if you want to get the vertex, you take the x coordinate of the vertex and you plug it in here to get the y coordinate, right? But I'm saying by f of 3, I'm saying that tells you to plug 3 in for x, okay? That is then 3 negative 2 times 3 squared plus 12 times 3 minus 10 equals 3. And you can do the arithmetic. That's going to be negative 18. That's going to be a negative 10, which gives you negative 28. That's going to be a plus 36. So I believe the vertex is at the point 3,8. Make sense? If you know that much about quadratic functions, then you're going to do okay when you have a test that asks you to do this. Because next test will ask you to do this. Okay? Sometimes you don't get y-intercepts. The graph could be down below or it could be up above the x-axis. It wouldn't go through the x-axis, okay? So you still have an axis of symmetry, but you have complex number of vertices. Whether you understand that or not, it's a complex number. It's not a real number. So it's out there in the ozone someplace. But this thing is still halfway between them, wherever they are. okay? And that's a little bit, yeah, you don't want to get into what that really means, okay? Just saying, just because you don't have zeros doesn't mean you don't have an axis of symmetry, okay? But if you don't have any zeros, you better know how to use this. And that's usually what you're going to do, okay? As a matter of fact, I'd say the way to approach the problem of graphing a quadratic function, you always get what you can out of the quadratic formula. So if you can find the zeros, find them, and you can always find the axis of symmetry. And the other thing you can always find, for example, if you knew the axis of symmetry and didn't know where the zeros were, you'd need another point on the graph. So I'm going to find a small board here. What's square? Well, I'm just going to do this. My brain isn't fully functional right now. So let's try to find a number here that would give you a non-real result where you got nice integer values. I can do that, but my working memory's just a little bit limited today, so I couldn't come up with it quickly. Okay, so anyhow, here we got this. So what we do is, well, kind of automatic. You find the zeros, the axis, symmetry, and the vertex. Well, doggone it, I didn't pick up a big enough number here. I don't know what's the matter with me. No, never mind, I did. And it actually came out even. Okay. Okay, well. So there it is. It's negative 12 plus or minus the square root of, well, that's 144. And this is minus 160. So that turns out to be negative 16. And the problem with that is square root of negative 16 is not a real number. Since it's not a real number, there's no x-intercept. Okay, well, we can still find the axis of symmetry. And x equals negative b over 2a, which is not a formula I recommend you memorize, although it's a pretty easy one. Why clutter your brain with an extra formula when you can just look here and see what it is in the quadratic formula, which you need to know. Okay. Although if you want to clutter your brain up, well, it's okay. It's already cluttered up with a bunch of stuff, you know. Anything like mine, it's a mess. But try to keep things straight, at least with the mathematics. Okay, so x equals negative b over 2a, which is negative 12 over 2 times negative 4, which is 3. Same as for this function over here. The only difference between this function and this function is I subtracted 20 here from negative 2x squared plus 12x, or here I just subtracted 10 from negative 2x squared plus 12x. Well, you can't see that, but in the previous function, this was a negative 10 instead of a negative 12. What's that do? That lowers the graph because I'm subtracting a bigger number from the y value. For given x, I get the same thing here as I'd get if I had a negative 10 here. So we're taking a quick look. So I started with this function, and here's its graph. In the axis of symmetry, well, we've got the vertex. And, you know, when I calculated the vertex, I never put the coordinates in there. But the coordinates are 3, 8. Okay. This is identical to this, except this has negative 20, where this has negative 10. Meaning whatever negative 2x squared plus 12x is, when I subtract 10, I get 8. That's the y-coordinate of the vertex. If I subtract 20, I'm going to get 10 less than 8, which is negative 2, which is going to shift the graph down below the axis so that there are no intercepts. Now that's worth understanding. Even though you can get answers to some of these questions without understanding that, gives you more perspective, it builds you a little better brain, and it could be very useful in understanding these graphs. So anyhow, axis symmetry is at x equals 3. Vertex is at 3, f of 3. In this case, that's at 3, negative 2. Okay, so we have a reflected quadratic below the x-axis. We can start to draw a graph of this thing now. Here's the y-axis, and here's your parabola. Try to draw it symmetric. And here's the line, x equals 3. And here's the vertex. Three, negative 2. Still, we don't have a scale for this graph. If we have the two x-intercepts, we have a scale for the x. And once we have the vertex, we've got a scale for the y. Well, we do have a scale for y. That much is 2. There's 2 y units there. What are we going to do? Well, what we're going to do is we're going to find the y-intercept. Okay. So the y-axis is somewhere the y-intercept is at y equals -20. Where's -20 on the y-axis? If that's -2, -20 is 10 times lower. I actually didn't draw the graph quite accurately, but we can say, okay, kind of suspend our disbelief again and say that, okay, this is y equals -20, whereas this line here is y equals -2. Really, -20 should be much lower than that, but I didn't leave myself enough room to do that. I can draw a better graph. I'll draw one over here. This one. Okay, so x-axis up here pretty high like I did here because I know that the graph is going to be below the x-axis. And I'm going to put this information, y equals -20 on the horizontal line here. And then I want my vertex at 3, -2. Okay, so I'm going to draw a line for x equals 3. And then I cut that in half, cut that in half. That's about 2.5. So I'm going to say that y equals -2 is about here. So my y-intercept is here. My vertex is here. And now I can draw a parabola. Now, if you're in my class, you'll see that we could draw a rectangle from here up to here, over here, and down here, symmetric with this line, and do an actual construction. The way we've learned in my class to construct a pretty accurate parabola, okay? But that'll be sometime probably next week or even the following week when we actually get to this in my class. Other classes are getting to this, so I want to make sure everybody has this background and has this picture, because if you do, I think it's going to make these sectional quadratic functions real clear, very clear, I hope. In my opinion, and everybody's got their own opinion, but in my world, I consider the sectional quadratic functions to be the most important in the whole class, because quadratic functions come up a lot. It's real important to understand them. There are other sections that are nearly as important. You know, you could argue, and I also say the section of transformations that my class had for homework today is extremely important because this is a transformation of your toolkit function. Most of the functions we see are transformations of toolkit functions, so we know what they look like and we can better deal with them knowing that. Anyhow, it's just my perspective on what's important in the course. Those are things that are highly applicable. And then exponential functions are really important too. So anybody that says that one of those is most important, I'm not going to disagree with them at all. I just say, well, yeah, I kind of think it's quadratic functions, but what you think is just fine. Now, if they think that it's linear functions, I'm going to argue that linear functions is something people should know before they come into this class. Anyhow, there it is. And that's a nice, neat little bundle for quadratic functions. Okay. If we look at this graph, we can see, first of all, we simply know we could prove it, but that's unfortunately beyond the scope of the way we teach pre-calculus now. We could prove that any function of this nature is a parabola, okay? And we could define a parabola. And the fact that we're not doing that, I find disturbing, but anyhow, I mean, it really is. I think it's a tragedy. Anyhow, we know this is a parabola, so it has to be a shifted and stretched or compressed toolkit function, right? So how is this related to the toolkit function? Toolkit functions y equals x squared. I'm going to draw a little rectangle here. Actually, a square. And put a y-axis through here, an x-axis through here, and then just sketch a parabola. I didn't get the y-axis right in the middle, so it's already a little lopsided, but that represents a toolkit function. And if you do as open math tells you to do, you're going to use x equals -2, x equals -1, x equals 1/2, x equals 0, and so forth. And you're going to make a table, and you're going to get the same thing that those of you in my class learned to construct before you ever had to do arithmetic, okay? So you can get an accurate picture of that, but that's not what I consider really important right now. You have this shape, and there are the dimensions of it. You transform this to get this function, okay? To get the y equals -2x squared plus 12x minus 10 graph, stretch it vertically by factor 2. Flip it across the x-axis. The word is reflect. I'll just say flip. Use interchangeable words. Flip across the x-axis. And shift the vertex to what? 0.38. That makes sense? Now you can see that. First of all, the -2 is in front of x squared. That's why we know we're going to have to vertically stretch it by a factor of 2. And then flip it because it's a negative, reflected across the x-axis. Okay? That comes from the -2 in front of the x squared. Then we have to figure out where the vertex is. Okay. And we've seen how to do that in 2 cases. So we know if we shift the vertex to 3, 8, we got to shift it 3 units horizontally and 8 units vertically. Okay. So we've shifted 3 units horizontally. Eight units vertically. So in the notation that we use, I'm going to take this board away now and work backwards in the other one. Again, in the notation that we use, I'm going to move the board over. There's glare up here. I've got to do something about that. Hopefully I'll get that done later today. The picture then looks like this. I'm going to use a rectangle here. That's toolkit. I've abbreviated square because I didn't want to write quadratic. What do we do with that? This would be y equals x squared. We stretch it vertically by factor 2, which means that we make this rectangle twice as high, and we sketch a parabola inside that rectangle. And there is our parabola. Then we flip that across the x-axis. Now, if you're in my class, you're familiar with the red dot, so let's just track the red dot. That's the vertex for the squaring function. Okay, we flip it. Oh, God, that was such a nice looking F, and I messed everything up. And, you know, I'm putting those words where I'm going to want to draw my graph. So I'm just going to draw a little arrow there and draw my doubled rectangle here. And now the graph looks like this. And I've just put the word reflect up here because I don't want to put too much else there. Now what do I do? Now I got to shift it over 3 units and up 8. Okay. So find an appropriate color chalk and do that. Okay, so you take the red dot and move it over 3 units. That would be like to here. And then up 8 units. Well, this rectangle's 4 units high, so this one's 8 units high, so that would take it up here. There's my horizontal shift. There's my vertical shift. And now I've got my vertex, which is the red dot here. Well, when I move this point over to here, then up to here, so that now my vertex is going to be at the point 3,8, I take this rectangle and I move it over so that the red dot is here. I'm running shorter colors here, but I'll do this. At first, I move it to where the rectangle is here. So there's I shifted over 3 units. And then I shift it up. And I get my final graph, and I think I'm almost out of colors, but yeah, I've got this. So I flip it up, and I've got this yellow rectangle here, and here's my actual graph. So here it is flipped, reflected. Here it is in this pinkish red color. Shifted +3 in the horizontal direction. And now shifted +8 in the vertical direction. And this is the graph of y equals -2x squared plus 12x minus 10. X is 3,8. And the x-intercepts here and here are -1 and 5. No, not -1. 1 and 5. There's an x-intercept. And over here is an x-intercept. If the graph is extended, keeps coming down here, and it's very plausible from the picture that this should be at y equals -20. And there's your y-intercept. So we could extend the whole graph similarly on this side and see what it's going to look like. So we want to focus on the yellow graph. That's our final graph. And our white graph, which is a toolkit function, which gets stretched out, flipped because of the negative sign, shifted 3 units this way and 8 units this way, and there we are. And that's the graph that we originally drew, but it's kind of complicated by a lot of lines in here and stuff. Maybe a little hard to see, but if you do it yourself and draw it out, you'll understand. Okay, so I guess that piece of chalk is, oh, tight. Huh? Yeah, well, swim goes right in the center. I mean, that's a lot easier than a foul shot. There's no excuse for missing it. But I didn't loosen the shoulder up enough. Okay. Yeah, occasionally I'll miss too. Shoulder caught right at the end and caused it to go low and left. You can feel it. Okay, anyhow, What else was I going to say about this? Well, the rule. Your vertical stretch or compression factor, I'm going to say is the magnitude of A. Then reflect through the x-axis. If A is negative. So symmetry is out, is, I'll just say is, I write x equals negative b over 2a. It is a line. So that in this case, I could have x equals 3, and that's the axis of symmetry. And for any function, you know then where the axis of symmetry is. I want to be able to talk about this function, and that's why I write y equals f of x equals, because now I want to say, and let's see, I got limited room down here. Let's just come over here and say that the vertex it's at x equals negative b over 2a. But if you want to find the y coordinate, you plug that x back into the formula for the function. And I just abbreviate, plug it into the formula by saying f of negative b over 2a. That's something you need to understand. That just says plug whatever this is into this expression. Because it's obvious that if you have y equals ax squared plus bx plus c and x equals this, then to get the y coordinate on that line, you plug that number in. So there's your horizontal shift. And vertical shift is k equals f of that. I didn't say here, it was implicit. Start with the toolkit square graph, and then you do vertical stretch and compression and so forth. So the vertex stays where it is while you stretch it, stays where it is even if you flip it, just like it did here. Then it moves over this far. That's negative b over 2a because that's where the axis of symmetry is. And then you shift it up because on the axis of symmetry, you find the y coordinate by plugging the x coordinate into the function. Now, I've said that about 75 times already in one set of words or another. And I think I didn't quite have all this within the camera, but there it is. If you know that much about quadratic functions, it's good. Also, for the y-intercept is at 0 f of 0, which means you plug in 0 here and it's going to be c. In this case, if this is your equation. And of course, now that has nothing to do with the transformations. It's just that if you do these transformations accurately, that's where the zeros are going to end up. But you're trying to graph the thing, go ahead, get the zeros. If you got real zeros, that gives you something to grab onto. If you don't, you can still find the vertex and the y-intercept. Okay? So that's kind of what you need to know in order to understand the graphs of quadratic functions. And that's a big deal. If you understand it now, it's going to make things really easy for you when we start chapter 3. In between now and then, we got to do chapter 2, which everybody should know before they come into a pre-calculus class, but nobody does. Okay. Anyway, we do a few things that are a little more sophisticated than you would typically do in an algebra sequence. Let's say you have, okay, where y equals f of x equals x minus 5 times x minus 1. Okay. This is factored form. Your zeros or x-intercepts still occur when y is 0. And if y is 0, then this product is 0. And as I think I've probably mentioned before, when the product of two numbers is 0, that means that at least one of them has to be 0. So this equation splits into x minus 5 equals 0, or x minus 1 equals 0. So you get x equals 5 or x equals 1. Well, those are the same zeros that we have in the function that we did before, but it's not the same function because you're only going to get an x squared if you multiply this out. You're not going to get a 2x squared or negative 2x squared. Okay, so now we can begin constructing the graph. And there are the x-intercepts. Not only that, but the axis of symmetry is halfway between so we've got a lot of our familiar information already. Furthermore, y-intercept occurs when x equals 0 because the y-axis is the line x equals 0. So that's at 5. So we can go ahead and say, okay, well, just put y equals 5 here. We might have to rethink that in a minute, but let's just do that. Okay. And then if we want to do formal calculation, it's 1 plus 5 over 2, which is 3. And it's x equals which it used to, I'm sorry, kind of slopped it, but I'm going to leave it the way it is. There's your axis of symmetry. So the vertex it's at 3, f of 3. In other words, the x coordinate is 3. It's on the line x equals 3. And you plug 3 in to the function. And you get 3 minus 5 times 3 minus 1, which is negative 2 times 2, which is negative 4. I think, let's see, 3 minus 5 is negative 2. 3 minus 1 is 2, and that's negative 4. So I think that's right. So here's the y-intercept. If this is y equals 5, then y equals negative 4. It'll be down here somewhere. Not quite as far from the x-axis as y equals 5. Looks like I overestimated, but here's your vertex. Can I draw a parabola through these points? Well, yeah. Those points, you can see the parabola if you think about it. And if you draw it a few times, you'll learn to see it a little better. But the parabola is going to look something like this, right? But there's your graph. So if the thing is factored, you don't have to mess with the quadratic formula. You don't have to use the quadratic formula to find the vertex because you can just average the two zeros. And there you have it. So that's very useful. There's one more thing. I'll warn you, the first problem, I'm probably going to want to watch the video to see how to do it. It's something to talk about a little bit more next time. Okay.